Hey, ladies and gentlemen, good morning. Welcome to episode 3 of Fighting for 5. All right, I want to start by saying something that I feel is important. First of all, I want to make it clear that these problems are here as a supplement to any additional studying you might be doing for the AP exam. Please do not think that just for the next month, you doing these 15 more problems at this point, 14 more problems, then you can just kind of stroll into the AP exam and get a 5. This is part of a supplement. You should definitely do your own studying. I've given you a whole bunch of resources where you can do like your own self-paced courses, stuff like that. And I will continue to give you resources. So please, ladies and gentlemen, I want to make that very clear. Don't expect to just finish these problems and expect to get a 5. Secondly, please watch the videos that I'm posting, because I understand that you might see the scoring guidelines and say, all right, yeah, great, I did this properly. And that's awesome. The thing is, many of these questions are kind of old, and the scoring guidelines change over the years. So during these videos, not only am I going through the problems, I'm also sort of indicating to you that, how you should give a full, complete response, so that no matter how they write the scoring rubric, you're guaranteed to get a full credit answer, right? It's weird. Sometimes the scoring rubric is written so that they focus on this piece of information, whereas the next year it might focus on another piece of information. So my goal here is to tell you how to write a complete response, so that no matter how they develop the rubric, you're going to get full credit. And lastly, I actually just wanted to make a correction to my previous video where for the binomial random variable, I forgot to mention that one of the very important conditions is that there must be a fixed number of trials. I did not mention that condition. All right. Anyway, let's get into this problem. This is an excellent problem because it shows us the difference between, just randomly selecting one object out of a population and finding a probability, and then randomly selecting a sample of objects out of the population and finding the probability of an average value. So it's basically a population distribution versus a sampling distribution. All right, and we'll go through this kind of quickly, but I'm going to give you some tips about what the AP is looking for. So part A. Well, actually, just real quick, the important pieces of information is when functioning properly, the actual weight is normally distributed, mean of 70, standard deviation of 0.9 tons, okay? And then we have this little last sentence that says, if the mean is greater than 70, the loading mechanism is overfilling. Okay, so now part A says, if the filling equipment is functioning properly, what is the probability that the weight of the ore in a randomly selected car will be 70.7 tons or more? Show your work. Notice that they are basing this question on an assumption, and that assumption is that the filling equipment is functioning properly. This is important. This should seem kind of like, sort of like a hypothesis test, in the way that, remember, when we build ourselves a hypothesis test, we are making an assumption. We're carrying that assumption through the entire process. And then when we calculate our p-value, which is a probability of an event occurring, we are calculating that probability based on an assumption. So very important in order to guarantee yourself full credit is, if you're using a variable, define it. Define it, define it, define it. And of course, you should use units. You can decide to use units in the definition or in the distribution that you name. So don't just define the variable, but define its distribution. These are key steps. All right. Now, once you've done that, we can just rely on the calculator. In this case, it's going to end up being normal CDF to get our probabilities. And so that's the whole point of showing this initial work, so you don't have to show any really strict additional work. Of course, use P notation. I'm just literally translating the question to the P notation. We're looking for the probability that X is greater than 70.7. A lot of you emailed me concerned about the Z-score situation that they showed in the scoring rubric. You can do it. It is not required. All right. And by the way, you might be wondering why we're using the normal distribution and not the t distribution. The major difference here and why we're allowed to use the normal distribution for these means is that, well, I guess this really applies to part C when we're talking about a sample. But the thing is, here we know the population standard deviation. And in a hypothesis test situation, that information is typically not known, which is why when we do a hypothesis test, we have to rely on the t distribution. But anyway, for today and for this problem, we're given all of the population info, and so we can use the normal distribution. All right, so there you have it. That's your probability. I ended up using normal CDF. Part B then goes on to ask, suppose the weight of an ore in a randomly selected car is 70.7 tons. So in other words, they're saying, suppose you actually observed that some car had a weight of 70.7 tons. Would you take this as evidence that the loading mechanism is overfilling the cars? And then you have to justify your answer. So I went on and wrote that since 70.7 tons or greater happens 21.83% of the time, even if the mechanism is working properly, this would not cause me to believe that the mechanism is broken. You can think of this as sort of like a p-value, and this p-value is much greater than any proper alpha value, right? We've been choosing alpha, a typical alpha value of about 0.05. So the fact that this p-value, quote unquote, is much greater than 0.05, then we would, in essence, fail to reject H null. Well, what is H null in this case? H null is that the mechanism is working properly, right? We're running along the assumption, with the assumption that the mechanism is indeed working properly, right? And so if that's the case, well, then this event would occur 21.83% of the times. So 1 out of every 5 times you'll have a car filled with 70.7 tons or more. Not that crazy. All right, part C. If the filling equipment is functioning properly, what is the probability that a random sample of 10 cars will have a mean or weight of 70.7 tons or more? All right, so things change now, because now we're not just studying a single car and finding the probability that that single car has a certain weight, but we're taking a random sample of 10 cars and we're finding the probability that that random sample of 10 cars has a mean weight of 70.7 or more. So this is a sampling distribution of sample means. So I'm going to define a new random variable, XBar, to be the average weight in a random sample of 10 cars. XBar is going to be distributed normally, mean of 70 tons, and a standard deviation of 0.9 divided by radical 10. This is the central limit theorem at work. Okay, I just want to remind you why the central limit theorem says that the expected value of X bar is equal to the expected value of X, and why the standard deviation of X bar is equal to the standard deviation of X divided by radical 10. So I'm going to derive those two concepts now. So here's your side note. Expected value of X bar can of course be written as the expected value of, well, the sum of your 10 X's divided by 10, right? That's how you calculate an average. Sum your 10 numbers up, then divide by 10. By the rules of expected values, I can pull out the constant, which in this case is 1/10. And so we have 1/10 times the expected value of X1 plus blah, 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 all the way up to X10. Okay, in your next line, This expected value of x1 plus blah, 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 plus x10 can be written as expected value of x1 plus expected value of x2 plus blah, 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 expected value of x10. Or in other words, it can be written as 10 times the expected value of x. So we have 1/10 times 10 times the expected value of x. And of course, that just simplifies to the expected value of x. So that is the derivation of why expected value of x bar is equal to expected value of x. For standard deviation, I, of course, start with variance, and then I'm going to eventually find the square root of the variance to get the standard deviation. So variance of x bar, similarly, I'm going to, instead of writing x bar, I'm going to write it as the sum of 10 x's divided by 10. That is how you get an average. The rules of variance say that if I have a constant and I want to pull out the constant, I can pull it out, but I have to square it. So I have 1/10 squared times the variance of x1 plus blah, 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 plus x10. Okay? And variances of x1 plus blah, 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 plus x10 can be written as a sum of variance of x plus variance of x2 plus variance of x3, so on and so forth. Very similar to what we did with the expected value. This is what's nice about using variances. So variance of x1 plus blah, 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 x10 can be written as 10 times variance of x. So here on this line, I have 1/10 squared times 10 times the variance of x. And of course, this simplifies to variance of x over 10. Now that's the variance of x bar, but I want the standard deviation of x bar, so I'm going to take the square root of both sides. Standard deviation of x bar is then equal to radical of the variance of x over 10, which of course simplifies to standard deviation of, standard deviation of x, standard deviation of x over radical 10. All right, so that's the derivation of this fact right here. And now we're going to use this once we have the distribution. It's very easy to calculate a probability. So the statement is, what is the probability that x bar is greater than 70.7? And of course, in this case, we get 0.007. So this is kind of interesting when we just are observing one car at a time. If that one particular car has an ore weight of 70.7 tons or greater, this doesn't seem like too rare of a situation. That happens about 1 in every 5 cars. But if we're looking at a group of cars, and on average that group of cars has 70.7 tons or greater, then we have cause for concern, because that should only happen 0.007 of the time, or 0.7% of the time. So that's a very, very, very rare occurrence if the mechanism is working properly. And this is what leads us into part D. But before that, a word from our sponsor.
Hey, wake up. What? Listen. Hey, what are you doing?
Kids, go back to sleep.
Why you?
That was close.
Now, where were we?
One taste and you're in love.
Welcome back, and those definitely look like a couple of satisfied customers. Okay, moving on to part D. Similar to part B, based on your answer in part C, if a random sample of 10 cars had a mean ore weight of 70.7 tons, would you suspect the loading mechanism was overfilling the cars? Justify your answer. Okay. So very similar again. We start out with a statement very reminiscent of interpreting a p-value, because this is essentially what we're doing. We're assuming if the mechanism is working, then the event of a selection of 10 random cars averaging 70.7 tons or more happens 0.7% of the time. If this event occurs, I would suspect that something is wrong with the mechanism. All right, so this would be a complete answer. Notice I'm using context I'm citing my answer from the previous problem, and I'm making a decision and basing that decision off of the information that I've gathered. All right, ladies and gentlemen, I'm going to end here. So please, 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 please watch my videos in the future, because I'm going to try to give you good information to get a 5. And this is not information you can get just from reading a scoring guideline, because they do change from year to year. All right, folks, have a great weekend. Take care, everyone. Bye.